The foundation of planetary model is obvious. In solar system, the gravitational force between the Sun and a planet is inversely proportional to the square of the distance between them. This force serves as the centripetal force, so that the planet revolves around the Sun. The electrostatic force between the nucleus and an electron is also inversely proportional to the square of the distance between them. Thus, the electron should revolve around the nucleus just like the planet around the Sun. However, is it really that simple? The planetary model involves a technical difficulty. The laws of classical electrodynamics show that an accelerating point charge releases energy in the form of electromagnetic radiation. Unlike charge-neutral planet, the electron releases electromagnetic radiation while orbiting a nucleus. Because the electron would lose energy, it would rapidly spiral inwards, collapsing into the nucleus on a timescale of around 16 picoseconds. The planetary model is disastrous because it predicts that all atoms are unstable, which contradicts badly with the physical reality. Moreover, the revolving electron and the nucleus form a rotating electric dipole. The frequency of electromagnetic radiation is equal to the frequency of its revolving. The frequency of the revolving of the electron in a hydrogen or an hydrogen-like ion, that is, one nucleus and one electron, can be calculated using the equality between the electrostatic force and the centripetal force. This equation determines the revolving frequency as a continuous monotonically decreasing function of radius. As the electron spirals inward continuously from infinitely far away to the nucleus, the emission would increase in frequency continuously from 0 to infinity, resulting in a continuous emission spectrum. However, late 19th century experiments with electric discharges had shown that atoms will only emit light, that is, electromagnetic radiation, at certain discrete frequencies. For example, when the glow from hydrogen discharge tube is narrowed down by a slit and passes through a prism, the light exposes lines on a photographic film. The positions of the lines correspond to their wavelengths. They are called spectral lines. Hydrogen is not the only atom that has lines in its emission spectrum. In fact, all atoms have their own spectral lines. The discontinuous wavelengths in atomic emission spectra cannot be explained by classical theory. In 1885, Johann Balmer discovered an empirical equation, the Balmer formula, to calculate the wavelengths of hydrogen's spectral lines in the visible range. Here, B is a constant. N is an integer greater than 2. In 1888, Johannes Rydberg generalized the Balmer equation for the spectral lines of hydrogen from infrared to ultraviolet ranges. Here, Rh is the Rydberg constant. N1 and N2 are positive integers with N2 greater than N1. The Balmer formula is a specific example of the Rydberg formula when N1 is equal to 2. To overcome the problems of planetary model and explain the spectral lines, in 1913, Niels Bohr put forth 3 postulates that sum up most of his model. First, the electron in hydrogen atom revolves in certain stationary orbits around the atomic nucleus without radiating energy, contrary to what classical electromagnetism suggests. The stationary orbits have certain discrete distances from the nucleus. The electron cannot have any other orbit. This quantum atom model has been suggested by Arthur Haas in 1910. Second, the angular momentum of the revolving electron is an integer multiple, n, of the reduced Planck constant, where n is called the quantum number. This was suggested by John William Nicholson in 1912 during his study on solar and nebular spectra. Third, electron can only gain and lose energy by jumping between stationary orbits, absorbing or emitting electromagnetic radiation with a frequency determined by the energy difference of the levels according to the Planck relation. Though, unlike Einstein, Bohr stuck to the classical theory of the electromagnetic radiation and did not believe in the existence of photons, this assumption can be readily explained by photon theory. In emission, an atom transits from a higher energy level to a lower energy level, releasing the difference in energy between the two levels as a photon. In absorption, an atom transits from a lower energy level to a higher energy level, taking up the difference in energy between the two levels from a photon. Thus, both emission and absorption obey the conservation of energy. The calculation of the orbits of hydrogen atom and hydrogen-like ions requires assumption from classical mechanics. It is assumed that the mass of the nucleus is much larger than the electron mass, which is a good assumption. The electron is held in a circular orbit by electrostatic attraction. The centripetal force on the electron is equal to the Coulomb force. This equation determines the electron's speed at any radius. The total energy, mechanical energy, is the sum of kinetic energy and electric potential energy. It is negative and inversely proportional to radius. This means that it takes energy to pull the orbiting electron away from the nucleus. Then, use the assumption that the angular momentum is an integer multiple of reduced Planck constant. Substitute the expression for the velocity gives an equation for radius in terms of n. The smallest possible value of radius in the hydrogen atom is called the Bohr radius. It is the typical size of hydrogen atom. Due to its simple relationship with fundamental constants, it became the unit of length in atomic units. The energy of the nth level is determined by the nuclear charge number and quantum number. The lowest energy level of hydrogen atom, E1, is the total energy of an electron revolving around a proton at Bohr radius, which is about -13.6 eV. All the other energy levels can be expressed comfortably in terms of E1, the nuclear charge number and the quantum number. The energy of a photon emitted by an atom is given by the difference of two energy levels. Use the relationship between the energy and wavelength of a photon. The wavelength of the photon given off is given by the equation with the form of the Rydberg equation. The concomitant agreement of Bohr's formula with Rydberg equation as well as Bohr's theoretical prediction for the value of Rydberg constant was one reason that his model was immediately accepted. The emission spectrum of hydrogen atom has been divided into several spectral series, according to the values of N1. The Lyman series includes the lines whose N1 is equal to 1. All the wavelengths in the Lyman series are in the ultraviolet band. The Balmer series includes the lines whose N1 is equal to 2. All the wavelengths in the Balmer series are in the visible and ultraviolet bands. The Paschen series includes the lines whose N1 is equal to 3. All the wavelengths in the Paschen series are in the infrared band. Further series follow the same pattern and equation as dictated by the Bohr's model and Rydberg equation. They are increasingly spread out and occur at increasing wavelengths. For example, the longest wavelength in Balmer series can be calculated with Rydberg formula. For Balmer series, N1 is equal to 2. For the longest wavelength, N2 should be the lowest integer greater than 2, that is, 3. As a result, the wavelength is about 656 nanometers.